I'm Charles Wilson, Staff Product Cybersecurity Architect at Torque Robotics. This presentation will cover an overview of dynamic analysis. This diagram shows the overall AVCDL training path. If you're taking this training, it's assumed that you've already completed the AVCDL overview training, and additionally, that you've completed the Requirements Taxonomy, Security Requirements, Secure Design Principles, Apply Secure Design, Threat Prioritization, Secure Settings, and Secure Coding trainings. This training will cover dynamic analysis. Before sending people and new equipment out into space, NASA has them spend time at their Neutral Buoyancy Laboratory. This is a huge water tank used to simulate a low-gravity environment. It allows them to put people and systems through their paces. The reason for this is that the stakes are very high and there's very little margin for error. This system allows them to test specific aspects of the equipment that they created in situations where, should a failure occur, they're monitoring it and can respond quickly to make corrections before it ever sees the field. This is the role within system development that dynamic analysis plays. It allows us to select specific areas within the software, put them under particular types of stress, and look at how they behave in order to determine whether or not there are any issues that need to be addressed before we release the system. Before we get into the process of dynamic analysis, let's consider some dynamic analysis types and tools that are of interest within the context of cybersecurity. One of the main things that distinguishes dynamic analysis from static analysis is that dynamic analysis requires that we actually run code, where static analysis is simply reasoning on code. This is an important distinction when we think about the kinds of analysis that we do. We can consider things like code coverage. Are we actually exercising our code? We can think about concurrency issues. We can think about fault localization, which tends to be a more manual activity. We can talk about invariant inference, where we've got what appears to be complex code, but in actuality has a very simplistic and static behavior. We have memory error detection. We think about this a lot because if there are errors in memory, we'll have bad behavior. We can talk about performance analysis, where we're looking at how the system as a whole acts both in terms of time and resources. There's program slicing, where our interest is in how we make the program as small as possible and still have it do what it's supposed to do. And finally, there's a type of security analysis which is looking at the behavior of the code as it's running with respect to cybersecurity. Our focus is primarily on memory error detection. Let's consider what tools are available for that type of analysis. There are 5 tools that we're going to consider when we're talking about dynamic analysis memory error detection. These are ASAN, which looks at address management, MSAN, which considers memory initialization, LSAN, which looks for memory leaks, TSAN, which is concerned with thread management, and finally, UBSAN, which looks for undefined behavior. The SAN in all of these is short for Sanitizer. These tools are available for most platforms and tool chains of interest. We won't be getting into any more depth on these. That's left to other trainings. With the background material out of the way, we'll now look at the workflow involved in the dynamic analysis process and then examine each of the activities it contains. The workflow for performing the dynamic analysis process is broken down into 4 discrete activities. These are establishing the cybersecurity relevant settings, instrumenting the element, performing the analysis, and finally, conducting a triage of the issues identified as a result of this analysis. Let's now turn our attention to each of these activities that go into the dynamic analysis process. Our first activity in the dynamic analysis process is that of establishing the settings we'll use. The activity itself includes a development SME, a cybersecurity SME, and a DevOps SME. They're going to take the element, the build file, and the documentation, and establish a set of settings to be used. These will be put into an updated build file, and a security options qualifications report will be produced. If this diagram seems really information dense, that's because this is an encapsulation of the secure settings process, which we're not going to go into detail here about. Because we're impacting the build, it's important to consider the execution time and the footprint. The reason for this is that since dynamic analysis is part of the test suite to be executed, it may well be time-bounded. And so it's important to consider how that time bounding will be impacted by the addition of the dynamic analysis task. The same thing is true for the footprint. If you have instrumentation that's put into a test and attached to the element, regardless of what the scope of the element is, you may run into boundary conditions for the particular system the code is running on, and you have to be cognizant of that. Rather than rehash a subject that's been covered separately, here are some references to review secure settings in more detail. They are the Secure Settings Overview training video and the Secure Settings document, secondary document. The next step in the process is to instrument the element test. The Security SME and the DevOps SME take the element test and updated build file and construct an instrumented element test. It's important to emphasize that generally what we're doing is really overlaying an existing test with the instrumentation to allow the dynamic analysis tool to run against the element. In some cases, this step may be fully automated. That's to say that we have the build file with updated settings, we know the subject that we're going to be dealing with, and just let it go through its cycle and generate an instrumented element test. It may be the case that there is no existing test, in which case the test case needs to be written. Either way, it's important to recognize that tests don't magic themselves into existence. The third activity in the dynamic analysis process is to perform the analysis. We're taking the instrumented element test, which will perform the analysis, and generating output. It's important to consider that we're generally not using just one tool, and a single element is not usually going to be the limit of our interest when looking at how a given tool performs against the system. With this in mind, we should treat all of our tools and all of our elements, where possible, as orthogonal. That's to say that when you're doing an analysis run, it's not covering everything. And by the same token, you want to make sure that multiple runs will yield you the coverage that you want to see. So it's important that there be some temporal coupling in these analysis runs. The reason for this is that the codebase is not static over time. It's important that when you're analyzing an element, that you're analyzing it to the extent that you're able with multiple tools, and to that end, it's important that you do so in a timely fashion. You don't want to do a dynamic analysis run that's looking at a particular aspect of memory initialization and then wait 3 weeks before you look at memory leaks, because these are related and coupled activities. Also, it's important to consider that because the code changes, that were you to do a memory leaks analysis a long time after you've done the memory initialization analysis, that you're possibly going to have new issues from the analysis that you ran first. The final activity in the dynamic analysis process, as with so many AVCDL processes, is that of triage. The cybersecurity SME and their development SME counterpart will take the analysis output and triage it. The issues found to be valid are placed into an identified issues list, which is then sent to the threat prioritization process, and a dynamic analysis report is generated. Some may consider having to put each issue through the threat prioritization process as excessive for issues which typically result from execution termination. Depending on how the organization implements their processes, it's possible that issues may be entered directly into the issue tracking system instead of passing them to the threat prioritization process, where the nature of the issues is unambiguous. Additionally, if you're performing a triage and discover that a tool is reporting an excessive number of false positives, then you should review the settings being used and ensure that they're appropriate. If necessary, remove those settings which yield incorrect results. Don't consider settings to be locked down, because at some point those settings may need to change. When we consider what goes into the identified issues, and in fact into the dynamic analysis report by extension, there are 3 fundamental pieces of information that need to be there. The first is the tool. This may seem a bit on the pointless side, but you have to consider that there's not just one dynamic analysis report that will ever be generated. There are a multitude of them. And so, as this information is entered into the issue tracking system, and as it goes through the threat prioritization process, Even as it's read, it's critical to know what tooling is being used. This extends beyond just the name. There are a whole host of pieces of information needed to identify what was used to perform the analysis. The next thing to consider is the documentation of the element. You may have gone through the exercise of deciding what the scope is and instrumenting it and such, but as it's conveyed from the process to other individuals, it's important that it be documented in a way that allows others to easily locate it. Finally, we have the actual results. In the case of dynamic analysis, as opposed to other types of analysis we do, the results may contain only one issue because by nature dynamic analysis runs to failure. The takeaway is that you need to make sure that we're including all of the information necessary for someone to both replicate and resolve the issue. That's an overview of the process used in performing dynamic analysis. Now, let's review what we've covered. As we've seen, the dynamic analysis process is fairly straightforward. We're going to start by selecting the tool or tools we're going to use. We're going to make sure that we're instrumenting appropriately so that we're getting the tool to give us the type of results we're interested in. Once we get the results, we're going to triage them. And finally, we're going to report those findings in both human-readable and machine-readable form. The latter because we want to automate our processes where possible. For more information and to get a more in-depth set of references, the Dynamic Analysis Report secondary document is available in the AVCDL GitHub repository. All AVCDL materials, both in source and distribution forms, are available on our GitHub site, as shown here. Because of the size of the repository, it's recommended that you either clone the repository or download a zip archive of it if you're not familiar with using Git. Instructions for downloading a zip archive are linked to on the repository's front page. Videos covering various aspects of the AVCDL are available on our YouTube channel, as shown here. It's important to note that all AVCDL materials, except for the introductory blog posts, are intended for product cybersecurity engineering practitioners. With this training complete, you can proceed to the other trainings at this level. These include static analysis, fuzz testing, and secure code review. Here are the references to the source material used in the creation of this presentation. They'll also be included in the video description. Additionally, this presentation's source material will be provided on the AVCDL GitHub repository.